Okay, now that's kind of it for Newton's method, not too much about that. What we do really want to start talking about is this idea of related rates. So this is, again, kind of like what we did last time with the differential, is we're trying to treat these as variables, just like we would an x or a y or a w or an L, and try to solve crazy equations and get these dy's over dt's to show up for particular things. To do it, you have a 6-step process. First, take the time to really figure out, okay, what is the rate we are seeking? What variables do we know? Just start naming things and listing things. And then 2, it's really easy to skip this step, but don't. Draw a picture and start putting things where they belong in that picture. Steps 1 and 2 are going to help you understand what is going on with that problem. We don't have any plans for solving it yet. We're just trying to fill in what we can. We might go back to the model and readjust it and add more things later, but we want to get a good model for what's going on in this problem, and so we can visualize what it's asking us when we're trying to do. Then write an equation. If that equation has everything in it, great. If it doesn't, then you can start with a basic one like we did before with optimization, and then add stuff to it in order to get all the information that you have in your problem into it. Be careful that you don't put all the numbers into it. Notice that that happens in step 5. Don't put all your numbers in. If you do, it gets rid of the idea of the fact that it is changing and things are changing over that time, and that's really what we're interested in. Calculus is the study of change, and we can't see if things are changing if we get rid of the variables. So we want to keep those variables. Then what we're going to do is a lot of these are going to be talking about time as we go into the future. So then we're going to differentiate with respect to time, t, and none of our variables are going to be t, and that's going to be okay. So we're going to end up with a whole bunch of things that are like ds over dt and dv over dt, but everybody's going to be over dt, and that's okay, because we're going to also know what some of those dv's over dt's are going to be. After you've done that, now's the time to plug in our numbers. So in step 4, we probably have a lot of variables. In step 5, that's when we start narrowing it down so we get one particular dv over dt that we're trying to find. Then we end with interpreting that solution. So it's like, okay, we got this number. What does that number mean? That's one thing that AP is going to be really interested in, is knowing what does that number mean in terms of your problem, giving it correct units, talking about it appropriately. All right, so we've got a heating plate. When a circular plate of metal is heated in an oven, its radius increases at a rate of 0.1 centimeters per second. At what rate is the plate's area increasing when the radius is 50 centimeters? Okay, so we first want to identify some variables of what's going on. So that is my step 1. I want to figure out, I want something about radius. So I'll probably use R for the radius of the plate. And the only other thing that we're really talking about is area. So how big this plate is. So we'll do the area of the plate for A. Okay, so there's something about radius and there's something about area. That's mostly what we're talking about. Everything else is kind of talking about a particular change. So let's get, now I think it's time for a diagram. So we've got this plate. So there is my plate, and it's got a radius on there. Cool. I know what the radius is. They told me that. They told me that this is 50 centimeters from right there. And then I also know this particular rate for the radius. So I know that it is a change in radius with respect to time. The change in our radius, as we have a change in time, equals 0.01 centimeters per second. Okay, great. Now, that is all the information that I know. Uh, what what is this problem even looking for? What rate is at what rate is the plate's area increasing? So what does that mean? So I want to know what the change in area is with respect to time. At what rate is the plate's area increasing? What is the change in my area with respect to our change in time is what I'm trying to figure out. Okay, so I've drawn a cool diagram. I know the radius is 50 centimeters. I know a particular rate that it's growing. I want to know how the area of the plate is growing. So I want to try to figure out what this green conglomerate is. All right, let's move on to step 4. Step 4 is asking us to create an equation. It doesn't have to be perfect to start off, but I want to start with like an area of a circle. Area of a circle is pi r squared. And I want to check if there's any other particular bits of information I could bring in there. I've already got A, I've already got R, I have that 50 centimeters, and I have that dr over dt. I don't want to bring those in right now, because if I bring them in right now, then I'm not going to get a dr over dt, and it's going to freeze that plate in place. I want to talk about how it is changing. If I put in a particular radius right now, it's not going to change anymore. It's stuck at 50 centimeters and it can't get any bigger or smaller. I want it to get bigger because it is getting bigger as it's heating up. So I want to keep it as an R right now. That'll change in a little bit. That'll happen in step 6 or something. Step 6. Yeah. So in step 5, I want to take the derivative of this thing with respect to t. So I'm going to take the derivative of both sides with respect to t. Notice that neither of my variables are t. So all of them are just going to kind of do our implicit differentiation, like when we did the derivative with respect to x and we had a y sitting around there. So that thing is going to happen with both of these variables. The derivative of a with respect to t is just the derivative of a over dt. Cool. That's the thing that we're trying to find. Oh boy, oh boy. Okay, let's do the other side. Let's see if I can take this derivative appropriately. I want to bring the 2 down. So I bring 2 pi r. And remember, I'm taking derivative with respect to t. I'm not taking derivative with respect to r. So I also need to take the derivative of r, kind of implying a sort of chain rule. So I get a dr over dt, which is good. I know that. It's 0.01 centimeters per second. Great, because now we're ready for step 6. In step 6, we're going to put in some of the numbers that we had gotten earlier that we haven't included yet. So I'm trying to figure out what dA over dt. I'm real excited. I'm going to make the colors match now. dA over dt equals 2 pi. The radius of my plate at the particular time that I'm interested in is 50 centimeters. And I know the dr over dt. At that time, it's changing at a rate of 0.01 centimeters per second. So 2 times 50 is 100. Times 0.01 is just 1. So dA over dt equals pi centimeters per second. But this is an area, and an area changes in not centimeters, it changes in square centimeters. So it's gaining pi centimeters squared per second. Now, that's not enough to say that we're done. We need to like write this out. So at the instant, at the moment in question, I feel like Porky Pig. You could also say when the radius has 50 centimeters, when the radius of the plate is at 50 centimeters. The area is increasing at a rate of pi centimeters squared per second. We want to write that sentence out to describe our answer. Don't, that's no good. Sorry for a quick change, but here is another example that we're going to work through. Now, this one has a little bit more players. Sand falls from a conveyor belt at a rate of 10 meters cubed per minute on top of a conical pile. The height of the pile is always 3/8 the base diameter. How fast are A, the height and radius changing when the pile is 4 meters high? Oof. All right. Let's identify some of the major players to identify what sort of variables we are going to be playing with. That's always our start. We have the height of the pile. We'll have that be h. Now, there is also the base of the diameter, so we could also talk about the diameter of the pile, but I'm also looking at part B, and they're probably talking about radius too. And radius and diameter are related problems. And in fact, actually, height and radius seem to match a little bit more with each other, and they're involved for the equation for the volume and diameter. So I'm going to go with radius rather than diameter. If I can spell it right. We can still add on D for the diameter of the pile. I might need that. And they are also talking about the volume of the pile. We can see that because it's got that 10 meters, cubic meters per minute. So that is probably involved too. So I'm going to use V for the volume of the pile. All right. Now, hopefully you've got your book open, so I don't need to like scroll up. I've got my like kind of cheat notes over to my left. Oh gosh, I got my cheat notes over to my left, so you could have seen that in a quick second there. So now I want to draw a picture of what's going on. So I've got this cone. There it is, very nice. It has a height. So here's our H, and it's got a radius. R. It's got a diameter D, so that's kind of like going around the base of that thing. And it's also got a particular volume. I know that the height, well, here, also on top of it, there is sand being dumped on here. So, sand. So that is sand being added to the top, and it's coming at 10 cubic meters per minute. So that is how the change in the volume is happening as time changes. Next, we should probably get that 3/8. So there's that relationship between the height and the diameter. So we know that the height is always 3/8 the diameter of the pile. And we can make this included with radius. This is what I was talking about earlier, because our diameter is always 2 times our radius. I was doing that wrong. Diameter is like all the way across. Doy. I was thinking circumference. I was thinking diameter as circumference this whole time. All right. So we could rewrite this equation as r equals 4/3 times our height to kind of just clean things up a little bit. All right. That is all the information that we have for our problem. Now it's time to identify, okay, what are we looking for? What are we looking for in this problem? We can find that usually right at the very, very end. How fast are the height and radius changing when the pile is 4 meters high? Oh, we forgot about that. When h, we're interested when h equals 4. Okay. All right. How fast are the height and radius changing when the pile is 4 meters high? So there are two rates that we're interested in. We are interested in the change in height at that particular time, and we're also interested in our change in our radius. So we want both of those things for our problem. Okay. Next, 4. We need our equation for the volume of a cone. And I had to look this one up. I didn't know this one off the top of my head. So it is 1/3 pi radius squared times the height of our, whatchamacallit, of our cone. So the volume of a cone is 1/3 pi r squared h. Okay. Now we can like clean this problem up a little bit so that we're not taking the derivative with as many variables. If we could implicitly differentiate this thing right now, we're going to have to do product rule and all kinds of other things, but there are either easier ways around that. So let's bring in this idea that r is 4/3 times the height and plug that in right here. So then our equation looks like volume is 1/3 pi 4/3 our height, just to make our lives easier. So if we simplify this thing, volume equals, I'm gonna get this as one big fraction. So 4 gets squared, and that's 16. Pi will be in the numerator as well. We've got an h squared and another h, so we end up with h cubed over, we've got a 3 squared in the denominator, which is 9, times another 3 from over here. So that is going to be 27 in our denominator. Oh, don't you crash on me. 27. Okay. Now we are ready to implicitly differentiate this bad boy. So that is step 5. Notice again, I did not bring in that height of 4. I don't want to do that yet. I did not bring in that dv over dt. I want to be bringing in all those numbers at the same time. So I want to take the derivative of v with respect to time. So that makes dv over dt equals, I'm going to break that 16 pi 27. I'm going to treat that as a coefficient on my h cubed, and then bring the 3 in front. So we got 3 times 16 pi over 27. Otherwise, I'd have to do the quotient rule. Who wants to do that? H squared, and then I need to implicitly differentiate h, so I need to find the change in h over the change in time. Ooh, that's one of the things that we wanted. Great, great, cool. Now let's put in some of the numbers that we had. That is step 6. So dv over dt, we knew that from earlier, is 10 equals, I'm going to simplify this a little bit. We get 48 pi over 27. H we know, it's 4. That's the instant that we're checking. And then dH dt, that's the thing that we're looking for. I'll make it red so we can really see it. Like, ooh, that's the thing we want. dH over dt. Okay. So now it's just a matter of just kind of like plugging and chugging to get this thing all by itself. I'm going to bring that dH over dt, the thing that we're trying to solve first. It's going to equal 10 divided by all that gobbledygook on the other side. So 4 squared is 16, and if I grabbed my calculator, which I did earlier, I'd get 16 times 48, which is 728 pi. Over 27 when I divide it to the other side. And then this ends up equaling, no, don't go to the next page. Sorry. 45 over 128 pi meters per minute. Yep, and I do want to make sure that it is meters per minute because height is a length and it's not going to be like meters squared like we had in the last one. Ooh, but my answer is expected to be in centimeters per minute. If you look at the problem, it says, and give your answers in centimeters per minute. So we want to convert that into centimeters per minute by multiplying by 100. So 45 times 100 over 128, because there's 100 centimeters in a meter, equals 1125 over 32 pi centimeters per minute. So that's my first answer, because remember, we also have to find dr over dt. To find dr over dt, we can actually use this, we can actually use this sub-equation that we had earlier. We can use this one and implicitly differentiate that with respect to time. Now that we know what dH over dt is. So if we take the derivative of this thing, we get dr over dt equals 4/3 dH over dt. Ooh, and I might as well use my centimeters version to find dr over dt. This equals 4/3 times 1125 over 32 pi, which equals 375 over 8 pi centimeters per minute. So you'd finish up by saying when the pile is 4 meters high, the radius is changing at 375 over 8 pi centimeters per minute. You could also maybe represent that as a decimal, but I know the exact answer, so I'm going to give the exact answer. And the height of the pile is increasing at a rate of 1,125 over 32 pi centimeters per minute. Oof. And that's it for today. It might have been a long time ago, but remember Newton's method. Newton's method is a quick way of kind of like checking how the calculator figures out these exact values. And then remember the 6 steps of evaluating these related rates. Number one, get those variables. 2, draw a picture. 3, write an equation and identify what is the thing that you're trying to find. 4, differentiate both sides implicitly with respect to time t. I think I was actually doing that as step 5. And then our step 6 was substitute. I kind of added an extra step. So sue me. And then finally, interpret your solution. Really make sure that you're saying what that value means. Don't just say, my answer is 11, or my answer is 11 feet per second. That's not what AP is looking for. It's looking for you to say, at a particular time, this is what's happening, and this is our rate with correct units. Thank you so much for watching. Hopefully you check out that bonus video that's also posted on Schoology, and you have a good day. Bye-bye.